Welcome back to another video from the Math Doc. We're still focusing on multi-step equation solution, and in particular we're going to be looking at equations that have variables on both sides of the equation. So we're looking at equations where we have one side equal to the other, and on both sides we'll have our variables. So the variable shows up in both sides. In a previous video, I showed some examples and instructed how to solve this type of linear equation, and so I'll include the links below in the description so you can go back and take a look at those. If you're new to this channel, please subscribe, and let's get started. So in this video we will focus on word problems. So as always, when we have a word problem, we will have to write a model. We will identify the variable, right? We decide what our variable is. We'll look at what is not known and what is known and figure out what the question is, and using that we will translate the word problem into a mathematical expression that'll include an equality so that we can then go and solve for our variable and answer our question. Once we have that linear equation as our model, we can then go ahead and solve it. Like in the previous videos, we will simplify. We will use the addition, subtraction, multiplication, and division properties of equalities in order to group similar terms. We'll have the variable terms, terms that include x in them, our variable, and we will have on the other side constant terms that include just numbers. So the constant terms that include numbers like 7, 14, and so on. So what we will try to do is basically, as always, our goal will be to isolate the variable so that we can see what it is equal to. And then after we solve, we always try to check our results. We first substitute the result directly back into our model, into our equation, in order to make sure that we solved correctly. But we also make sure that the result makes sense, because when we are working with a word problem, there's a story there. We are not just counting numbers, we are counting something, either maybe the average height in a classroom, or the weight of a car, or the number of apples in a basket. Whatever it is, the results should make sense. So let's get started right away. Let's look at the two problems we have here. So I wrote out both word problems, but we will work on each one of them separately, of course. And let's get started with this first one on the left. So what do we have here? Charlie makes sure to get enough protein for breakfast. He either has 1 cup of milk and 2 eggs. Let's underline that. 1 cup of milk and 2 eggs. First piece of information. Or a cup and a quarter of protein shake. Okay, so he has 2 different kinds of breakfasts. In both cases, he gets the same amount of protein, though the protein shake has 8 grams more of protein per cup. Each egg has 6 grams of protein, so let's underline that. 8 grams more and 6 grams. How much protein does a cup of milk have, and how much protein does he have each morning? Okay, so there's a lot of information here, and we will parse it slowly. We'll look at all the data we have. So first off, we know that he has 2 different kinds of breakfasts, but there is something in common. He always gets the same amount of protein. So what we know is that protein in breakfast 1 is equal to protein in breakfast 2. So that gives us already a framework of how to build our model. We can compare the protein in both breakfasts and see if we can solve that. Well, what else do we know? We know that in the first breakfast he has 1 cup of milk plus 2 eggs, right? And that should be equal to his second breakfast, which is 1.25 cups of protein shake. So I'll write that out as 1.25 cups protein shake. Okay, so now in a cup of milk, he has a certain amount of protein, and we don't know what it is. So let's just use that as our variable. So x, our variable, is going to be the protein in a cup of milk. Okay, what else does he have? He has 2 eggs, and we know that each egg has 6 grams of protein, so we can write 2 times 6. And that equals 1.25 cups of a protein shake, right? How much protein is in the protein shake? Well, we don't know exactly, but we do know that the protein shake has 8 grams more of protein per cup. So if the cup of milk has X grams, the protein shake has another 8 grams, and we have to multiply that by 1.25 cups because that's what he drinks in breakfast too. So let's write this out a little more neatly. Let's see, what do we have here? We have X, right? And times 1, that's 1 cup, plus 2 times 6 equals 1.25 times x plus 8. Okay, so this is our model, our new equation. Okay, it doesn't look that complicated, but it does have the variable on both sides of the equation. The first thing we like to do is to simplify, and we will do that by using the distributive property. The distributive property for opening parentheses. So here on the left-hand side we have x plus 2 times 6 equals, and now let's open these parentheses. We have 1.25 times x plus 1.25 times 8. That is the distributive property. Let's simplify this some more by writing out our fraction as an improper fraction. 1.25 is 5 quarters, right? Because 1 is 4 quarters, so we add that up. So now we have x, and we can do this multiplication, plus 12 equals 5 quarters of x plus 5 quarters times 8. Now we can simplify this fraction here. Since 4 goes into 8 2 times, we can write this as x plus 12 equals 5 quarters x plus 5 times 2. Okay, now let's start grouping or combining similar terms. Let's start with our variable terms. We have 5 quarters x here and 1x here. Let's try to transfer our x variable terms to the right. We can do that by subtracting x from both sides. So we're using the inverse operation to plus x by subtracting 1x from both sides. So we have x minus x plus 12 equals 5 quarters x minus x plus 10, where I've done this multiplication now. Okay, so now the 2 x's on this side cancel. Although they are variable and we don't know what x is, both x's are the same, and so they cancel. So we're left with 12 on the left. 5 quarters x minus 1x is 5 quarters minus 1 times x, right? Again, that's the distributive property, plus 10. We'll take it one step further, so we have 12 equals, now 5 quarters minus 1 is just 1 quarter, so 1 quarter x plus 10. Now let's combine the terms that are constant, the 12 and the 10. And in order to do that, we will use the inverse operation to plus 10 by subtracting 10 from both sides. Right? So we use the subtraction property of equalities, and we have 12 minus 10, which is 2 on this side, equals a quarter x plus 0, because the two 10s cancel. Finally, we have one more operation to do. We have a quarter here. So we're basically dividing x by 4 in order to remain with just x completely isolated on the right. We have to multiply both sides by 4. We do that, we get 2 times 4 is 8. 8 equals 4 times a quarter x, and these quarter and the 4 cancel, and our result is that x equals 8. So there's 8 grams of protein in 1 cup of milk. Okay, that's the first part of our question. We had a second part. Let's go back up and look at it. Okay, so how much protein does a cup of milk have? It has 8 grams, right? Which would mean that the protein shake now has 16 grams of protein, because it has 8 grams more per cup. So if the milk has 8 grams and each egg has 6 grams, we're basically looking at this side of our equation here. So what we get is that Charlie has 8 plus 6 times 2, which is 20 grams of protein for breakfast. So let's review this problem sort of generally, so we can review the steps we took. The first thing we did is we underlined all the information, the numbers that we got from the question. And then we figured out what we were missing and what the question was. We were essentially missing the amount of protein in a cup of milk. And we built our equation on the piece of information that was given about the two kinds of breakfasts. We knew that they both had the same amount of protein, therefore they were equal. So we solved this problem, and it would be a good idea to use a couple of minutes to actually check the result, and you can do that. You can stop the video and do that right now or a little bit later. But for now, we will go on to the next problem. So in this second problem, we have a runner who can run uphill in 25 minutes. Okay, running down takes her only 10 minutes because her speed is 5 miles per hour faster downhill. Okay, how long is her total run? So what do we know here? We know that a runner can run uphill in 25 minutes, and that running down takes her 10 minutes, and that her speed downhill is 5 miles per hour faster than uphill. And the question is, how long is her total run? So what we know is, we know that the time up equals 25 minutes. The time down equals 10 minutes, right? And that her speed, we don't know what her speed is, right? But we do know that speed down equals speed up plus 5. So she's way faster. What else do we want to know? We want to know her speed probably, and we'd want to know what her total run. So her total run is the distance up plus the distance down. Okay, so we don't know her speed and we don't know the distance. But we do know something about the distance. What we do know is that the distance up is equal to the distance down, right? She goes uphill and downhill, and we're not told that she takes a different trail. So we do have this part that is known, and we can use this equality to build our model. So how do we figure out what the distances are? Well, we can use something called the distance formula, which it basically says that the distance equals the time it took times the speed. Okay, so if we multiply the speed by the time, we know the distance. So how can we include that in our new model here? Well, we know the time up times the speed, let's write the speed as s, up, equals the time down times the speed down. Okay, now we know the times and we know something about the speeds, right? We know the difference between the speeds. So let's write that out. The time up is just 25 minutes and the time down is 10 minutes, right? So we have 25 times the speed up equals 10 times the speed down. But what is the speed down? We know that the speed down is exactly the speed up plus 5. So let's write that. We'll write it as speed up plus 5. Okay, so now we have a model, right, with one variable. Our variable is the speed up, which we will now write as just s, okay? We'll leave out the up there. So we have an equation and we can start looking at ways to solve it. So we have our variable s on both sides of the equation. So we're going to use the various tools and properties that we already know. So the first thing we're going to do, because we have the parentheses here, the brackets, we're going to use the distributive property. So on the left-hand side, we have 25s. Remember, I removed the up symbol just to simplify. And on the right-hand side, we have 10 times s plus, from there, 10 times 5. Okay, so we opened the parentheses. Now, we want to combine like terms. Let's start with the variable terms. So we have 25s here and 10s here. We can use the inverse operation to plus 10 by subtracting 10s from both sides. Okay? Let's subtract 10s from both sides. So on the left, we have 25 times s minus 10 times s. And on the right, we have 10 times s minus 10 times s plus 10 times 5. Okay, now again, s is our variable. It's the speed. We don't know what it is, but we know it's the same s everywhere in this equation. So we can say that if we started with 25s and we took away 10s, we're left with 15s. And that should equal 10s minus 10s is just 0. That should equal 50 because we can multiply 5 by 10. Okay, we have one more step in order to isolate our variable s, the speed. And that is to take the inverse operation to the multiplication by 15. So the inverse operation here will be division. So let's divide both sides by 15. And what we get is we get s times 15 divided by 15 equals 50 divided by 15. Okay, what is that? So now the 15 divided by 15 cancel. We have s, and s equals 50 divided by 15. Let's do that up here. 50 divided by 15. 15 doesn't go 0 times into 5, but it goes 3 times into 50. 3 times 15 is 45, and 50 minus 45 is 5. So we have 3 plus 5/15, right? We have a remainder of 5, and that is just 3 plus a third, or we can write that S, the speed up, is 3 1/3 miles per hour. Why is it miles per hour? Where do we get those units from? We get those from the initial problem where we wrote out our difference in speed in miles per hour. So we know her speed uphill is 3 1/3 miles per hour, and the speed downhill will be 3 1/3 plus 5. So that would be 8 1/3 miles per hour, which is really quite fast. Okay. Now the original question was, how long is her total run? Right here, right? How long is her total run? So let's go back and look at this. We have her speed. Her speed up is 3 1/3 miles per hour, right? And her time up is 25 minutes. So we have to convert one of these numbers into the same time units, because we have here minutes and here hours. So if we have 25 minutes in time, that would mean that per hour, in 1 hour, there's 60 minutes. So that would mean that she runs 25 divided by 60 hours, right? She runs nearly half an hour there. So it's 25 per 60 hours. So her distance, now we can write it out using the distance, remember, is the time times the speed. So her distance equals the time now is 25 divided by 60. And she runs 3 miles and a third per hour times 3 1/3. Let's play with this a little. The distance up, this is the distance uphill, right, which is just half the distance she runs. That is 25 divided by 60. Let's turn this into an improper function. That is 10/3. So we have 250 divided by 180. That's the distance she runs uphill. And we can simplify this fraction. So first of all, we can divide both the numerator and the denominator by 10. So now we have 25/18. That's the distance up. And let's write the total distance as the distance up plus the distance down. We know they're both equal, right? And they're equal to 2 times 25/18. So we can simplify this a little bit more. We can divide both the numerator and the denominator by 2, so we get 25/9, and that is equal to 2 plus 7/9. So the distance she runs, the total distance, is 2 7/9 miles. And again, we have this in miles because we gave our initial distance, our initial speed in miles per hour. And she runs a total of 55 minutes. So she runs nearly 3 miles in 55 minutes. And that makes sense. She's running more or less a 20-minute mile. But since she's running uphill, that's a pretty good time. So this concludes our video on word problems for linear equations where the variable is on both sides of the equation. I will include the links below to the background for this video And of course, I will follow up with more videos with more word problems for linear equations. They'll become slightly more complex as we go along, but we'll keep practicing the same tools, both to build the models and to solve them. So if you're new to the channel, please subscribe, like, any comments are welcome, and I hope to see you in the next video.